into our very last week. Here we go. So we're going to study two different things in this final section. We're going to study lamina. So a lamina is officially a three-dimensional object, but it's so thin that it can actually be treated as a two-dimensional object. So you're kind of thinking various different types of plates or plates that you cut, something like that. Basically, because they're so thin, if you want to talk about their center, you don't actually have to talk about their center of gravity. I mean, if you specify a point in the two-dimensional face, that basically gives it. So we're going to be finding the centroids of these, and then we're going to look at surfaces of revolution. So these are kind of like volumes that you'd make if you're using a lathe. So for example, something like this. So they'll have a symmetry to them. Now, as I said, they will have a symmetry. And so, I don't think I drew that perfectly, did I? It's nice. I can make a small change. Okay, something like that. Oh, that doesn't work either. Fake it. Sorry, so stupid. There we go. Okay, so what we'll be interested in finding the center of gravity on this. Because of symmetry, it will be on the central axis, but we want to find that. Now, we'll also have to find here the area, and here we'll also have to find the volume. Okay, so these are the two things that we're studying. Okay, so we'll start with the lamina. So imagine a region. Now it'll be, for us, it'll be under a function. Now there are, of course, different kind of types of lamina, but these are particularly easy, relatively easy to analyze. So we're looking at this region here and imagining that it's actually, in reality, it's three-dimensional, but we're treating it as two-dimensional. So the area is just the integral from a to b. That's something we've seen already. And the question is, suppose you want to balance it on a point, and that is the centroid. So there's a formula down below. Now, there is an appendix which derives these formulas. So this will be a thing where if you cut out the lamina, it has to be uniform density. It can't be like heavier in one place, denser in one place than another, that you actually could balance it on your finger. So this is the coordinates x bar, y bar, and that's the centroid. So if you want to see where these formulas come from, you can look at the appendix. So it's a bit where the, I think it's where the internal torques are zero. So what that means is that basically at any other point, if you try and balance it on your finger, it'll move. Okay. Yeah. So if you were doing an exam with me, an unseen closed book exam, I would actually give those formulas. You wouldn't be expected to learn those. Okay. So I think we're just going to do some examples. Now you do have to have an idea of what curves look like, but if you want, you can just plot. Actually, that's not true. You can just plot points. Okay. So yeah, as I said, if you know what curves look like, it makes it a bit easier. Like, so I know I can actually just go and do a rough plot of this. So we're looking the area between the curve 2x squared plus 3, the x-axis, and x equals 0 and x equals 3. So I know it looks something like this. Although, do you know what? So I do know the rough shape of these, but I think it actually makes more sense to actually plot the points. So normally it wouldn't in my head because I know what it looks like roughly, but here I'm trying to calculate something in particular. So yeah, maybe we'll plot the points. So let's look at x equals 0, x equals 1, x equals 2, and x equals 3. So we'll substitute those x values into 2x squared plus 3. So this one will get 2 times 0 squared, which is 0, plus 3 is 3. The next one is 2 times 1 squared, that's 2 times 1, which is 2, plus 3 is 5. And the next one is 2 times 2 squared, that's 2 times 4, which is 8, plus 3 is 11. And the last one is 2 times 3 squared, 2 times 9 is 18, plus 3 is 21. And if I had a little scale, it would be nice, but it doesn't have to be perfect. So maybe I'll do something like, say, 20, 10, 15, 5. Maybe that'll give me some kind of accuracy here. And then 3, 1, 2, 3. Okay. So I want to plot this thing. So 5. So we're back. So this is 5, 10, 15, 20, and 1, 2, 3. And let's plot some points. So we have x equals 0, y equals 3, x equals 1, y equals 5, x equals 2, y equals 11. So this is rough, this is fine. X equals 3, y equals 21. Something like that. And we're looking for this area here. Okay. Yeah, no bother. So how do you find area? You integrate. No bother, and we're integrating from 0 to 3. Okay, so the area here is the integral from 0 to 3, 2x squared plus 3 dx. So this is a fairly straightforward one. You can do it straight from the tables. So fix the 2. The antiderivative of x squared is x cubed over 3. And what do you have to differentiate to end up with 3? The answer is 3x. And now we just do top limit minus bottom limit. So we get 2/3 3 cubed plus 3 times 3 minus 2/3 0 cubed plus 3 times 0. Off to the calculator with that. And it'll be 27 or something. It's 2 by 9 plus 9, 27. Yeah. Now we'll see actually, can we approximate that roughly? So it's a good idea if you have a picture. So you know that the area is going to be less than the area made out of the rectangle and the triangle, because you can see it's less than it. So this has area 9, and this area is half the base, which is 3, and the height going from 3 up to 21 is 18. So that'll be 27. So the area under the big yellow thing is 36. So that means actually that there's 9 in here, by the way. So it's 9, 18, 9. Yeah, okay. That's not important. Actually, it's actually really not important. I'm just trying to remember that integration is giving you area. So if you can approximate the area, you can approximate the integral. Okay. Now we're asked to, and have we got space for this? Determine the centroid of this region. Okay. So we'll use these two formulas and look at the area, the integral of y. That's the same as the area, so we know the bottom of these. So the first thing we'll do is we'll find the integral of x by y. So remember, y is here in this question 2x squared plus 3. So we'll integrate, we're going to find the integral of x by y, and y is 2x squared plus 3, and we're integrating from 0 to 3. So this is equal to integral 0 to 3 x times 2x squared plus 3. So you can't do it in the table from the tables because they're multiplied together. So you need to try manipulation, and the obvious manipulation here is just to multiply it out. So you get x by 2x squared is 2x cubed, x by 3 is 3x. And now this can be anti-differentiated term by term. So fix the 2, what's the antiderivative of x cubed? X to the 4 over 4. Plus fix the 3, and what's the antiderivative of x? Well, I would say that x is x to the 1, and so its antiderivative is x squared over 2. Going from 0 to 3. And now we just do top limit minus bottom limit. So we get 2 over 4, 3 to the power of 4, plus 3 over 2, 3 squared. So that's substitute in the top limit minus substitute in the bottom limit. So you're going to get 2 over 4, 0 to the 4, plus 3 over 2, 0 squared. And we'll put the first thing into the calculator. So I have 2 over 4 by 3 to the 4 plus 3 over 2 by 3 squared. And I get 54. Now we'll be using that number a little bit later on. So we're building up these two formulas with a bit of yellow around them. So we've got that the integral of xy is 54. We've got the integral of y is 27. It is a bit of a fluke that they have such a nice relationship between them that the x bar is just going to be 2. Okay, now we need to look at half the integral of y squared. So I think we're just going to look at the integral of y squared. So we're integrating from 0 to 3, the integral of 2x squared plus 3 all squared. Now unfortunately you can't anti-differentiate this term by term because the thing is squared. It's not a sum of terms. So you have to try manipulation, and the manipulation here is to multiply 2x squared plus 3 by 2x squared plus 3. And if you carefully do that, maybe we'll do it over here. So 2x squared plus 3 by 2x squared plus 3. So the 2x squared by the 2x squared, the 2 by the 2 gives me 4. X squared by x squared gives us x to the 4. You have 2x squared by 3 giving you 6x squared. 3 by 2x squared giving us 6x squared. And finally 3 by 3 is 9. So you end up with 4x to the 4 plus 12x squared plus 9. So that's a manipulation. So this is equal to the integral from 0 to 3, 4x to the 4 plus 12x squared plus 9 dx. Okay, and now we'll anti-differentiate term by term. So fix the 4, and the antiderivative of x to the 4 is x to the 5 over 5. Fix the 12, and the antiderivative of x squared is x cubed over 3. And what do you have to differentiate to end up with 9? The answer is 9x. And we're going from 0 to 3. Now we do top limit minus bottom limit. So 4/5, 3 to the 5, plus 12/3, which is 4, times 3 cubed, plus 9 times 3. Substitute, minus substitute in the 0. So 4/5, 0 to the 5, minus 12/3, 0 cubed, minus 9 times 0. Now you might say, why did I bother putting in all those zeros? Because I have seen some people make mistakes assuming that if you have to substitute in 0 you get out 0. That's not always true. If you're dealing with cos or exponential, e to the 0 is equal to 1, cos of 0 is equal to 1. What does this come out as? So 4/5 times 3 to the 5 plus 12/3, which is 4, times 3 cubed, which is 27, plus 27. I'm getting 329.4. And now let's finish it off. So it says that x bar is equal to, this is the formula, that's, you know, you have it, it's in the manual. Integral of xy dx over integral of y dx. Integral of xy is 54. We found that up the top. And integral of y is the area, is 27. And that's equal to 2. And then the other one, y bar, is equal to half the integral of y squared dx divided by the integral of y dx. That's a half. What's the integral of y squared? 329.4. I know I'm going quite fast on this, but remember you can always pause me and rewind. And then the integral of y we found also was 27. So I'm going to bang that into the calculator. And out pops 6.1. So these are the coordinates of the centroid. Now what we'll do is we'll go back to the picture at the end, or at the start I should say, and put it in, and hopefully it makes some kind of sense. So x equal to 2, y equal to 6.1, something like this. Yeah, that makes a bit of sense. So that's the last thing you have to do. So sketch, find the area, find the centroid, and indicate on your sketch the position of the centroid. That's basically it. There's a few examples there for you to try, but that's the basic idea. There's a worked example there. Yeah, and that's one question I could ask.